this is lecture 4 of the course on vibration and structural dynamics. So, today we will talk about certain examples of underdamped free vibration response. So, let us go to the first example that we want to discuss in this lecture. So, as I said in the earlier lecture, most common form of damping that we encounter in real life is underdamping, okay, where the response of the single degree of freedom is still a oscillatory motion, but the amplitude gradually decreases with time, and the decrease in the amplitude follows an exponentially decaying curve. Now, I also said in the last lecture that the most common way of finding out damping of a system is through experimental analysis. So, the most common form of experiment that we do to find out the damping of an underdamped system is called the logarithmic decrement. So, now I will try to briefly explain what is logarithmic decrement and how do we find out the damping ratio or damping factor of a single degree of freedom system using logarithmic decrement. We will also use logarithmic decrement for the later part of the course, where we try to find out the damping of a multi-degree of freedom system. So, let us start with the response of a single degree of freedom system undergoing underdamped condition. So, what we do here experimentally is that at certain time instant t1, we measure the amplitude of the response of the single degree of freedom system of the system. Okay. So, say at t1 I measure the amplitude of the response of the system experimentally. So, experimentally we get the response, we can measure the response of a system using several sensors like accelerometer, even a strain gauge or other microelectrical mechanical systems. So, we find out the response at T1 and let me call it as U1. So, this is U1. Then what usually is done that after one time period, one complete time period, the amplitude is again measured. Okay. So, and let us call that as U2. So, we measure the amplitude exactly after one time period. So, we measure it at T1, which is U1, and then we again measure it after a time Td, that is at T1 plus Td, and let the amplitude there be U2. Now, what would be the expression of U1? We have already seen earlier that for an underdamped case, the response U1 can actually be written as A into cos omega dt minus phi into e to the power minus zeta omega n t. Okay. So, this is the response at t equals to T1, okay, where omega d is the damped natural frequency. Just to repeat that omega d is nothing but omega n into 1 minus zeta square, and this is called the damped natural frequency. We have already talked about this in the earlier lecture. This is just for a recap. Okay. And zeta is the damping factor or damping ratio that we are trying to find out through this process. Okay. Now, what would be the response at time T1 plus Td? So, we have called it as U2. So, U2 is nothing but A cos omega d into T1 plus Td minus phi into e to the power minus zeta omega n omega n T1 plus Td. Okay. Now, let us take the ratio of this two. So, let me try to find out U1 by U2. So, then in that case it is going to be A cos omega dt1 minus phi into e to the power minus zeta omega n T1 by A cos omega d T1 plus Td minus phi into e to the power minus zeta omega n into T1. Now, this Td is nothing but one time period of the response. So, that can be written as 2 pi by omega d, because this system is now oscillating with the frequency omega d, which is the damped natural frequency of the system. So, this equation therefore can be written as A cos omega d T1 minus phi into e to the power minus zeta omega n T1 by A cos omega d T1 plus omega d into 2 pi by omega d minus phi into e to the power minus zeta omega n T1 plus Td. Okay. So, here what happens is that this omega d cancels out with omega d. So, on the denominator I am just left with A cos omega d into T1 plus 2 pi minus phi into e to the power minus zeta omega n T1 plus Td. So, now what happens is this actually is the 2 pi thing will just give me again a same cos omega d T1 minus phi. So, this whole thing actually cancels out with this whole thing, and therefore, I am left with 1 by e to the power minus zeta omega n into Td. So, this also gets cancelled out with this part. So, I am just left 1 by e to the power minus zeta omega n into Td. Now, what I do is that I take the natural logarithm of u1 by u2. So, if I take the natural logarithm of u1 by u2, I have zeta omega n into Td, which is nothing but zeta omega n 2 pi by omega d. Okay. So, let me say that again, that ln u1 by u2 is now just going to be 2 pi zeta into 1 minus zeta square, because I got 2 pi zeta into omega n by omega d. So, this omega d can actually be written as omega n into 1 minus zeta square. So, this omega n will cancel with this omega n, and I am going to be left with this. Now, as we have discussed earlier, that for most of the real life system, zeta is very small, zeta is very much lower than 1. It comes in the range of like 0.01 and maximum 0.05. Okay. So, 0.05 is for rubber. So, zeta square becomes even smaller than 1. Therefore, this 1 minus zeta square for a lightly damped system can almost be written as 1 for a lightly damped system. Okay. So, for a lightly damped system where zeta is much less than 1, this can almost be said to be equal to 1. So, in that case my ln u by u2 becomes just 2 pi by zeta. Okay. I should actually call it almost equal to 2 pi by 2 pi into zeta. Now, this term is called the logarithmic decrement. This term, the term that gives me the log of the ratio of the amplitude at a time period away is called the logarithmic decrement and generally represented by this symbol delta. So, therefore, I can say that logarithmic is equal to logarithmic decrement is equal to 2 pi zeta, and therefore, I can find out the damping factor zeta as logarithmic decrement by 2 pi for lightly damped system. So, even if the system is not lightly damped, if we cannot say that zeta is very much less than 1, but of course less than 1, then also we can find out zeta in terms of logarithmic decrement by solving this equation. Okay. So, now, let me summarize that for an underdamped system in experiment, people measured the amplitude of the response at a time instant t1 and again measured the amplitude of the response just after one time period td, and then they find out the natural log of the ratio of these two amplitude, and the damping factor for a lightly damped system is this logarithmic decrement by 2 pi. Okay. This is the most common form of finding out linear viscous damping in a underdamped single degree of freedom system. So, let me just go to some more examples to clear the concepts of damping that we have learned. But before I go into example, I should complete the theory on damping by talking about some other forms of damping. So, all this while we have been talking about linear viscous damping, which is the most common form of damping and also the most simplest form of damping model. So, linear viscous damping is a common form of damping which is found in many engineering systems like instrument, shock absorber. Here, as I said earlier, the damping is modeled as the damping force is modeled proportional to the velocity of the body or the velocity across the damper, and it always opposes the motion. And as I said, because the analysis of viscous damping leads to simplest mathematics, many more complex damping are often approximated as a viscous damping. So, the other form of damping which is also common is called the Coulomb damping or the damping due to dry friction. Okay. So, this kind of damping is encountered in cases where two surfaces slide against one another, and the damping that results from the friction between the two sliding surfaces is called the Coulomb damping, and it is modeled using a nonlinear differential equation. So, the damping force actually comes out as a nonlinear function of the velocity or displacement. So, the other form of damping, the third form of damping, which is also often used by engineers is called the hysteric damping. Now, what happens in hysteric damping? That in theory we assume that when the body is being stressed within the elastic limit and we unstress the body or unload the body, then the loading and unloading path are similar. So, what we assume is that, so suppose this is stress and this is strain. So, we assume that within the elastic regime, while we unload, the path that we follow is exactly similar to the path that we follow while unloading. But in real life, this actually does not happen in many cases. So, where the loading path is not same as the unloading part, and the unloading part is slightly different from the loading path, creating a hysteretic loop. And this hysteretic loop actually dissipates some energy from the system and converts the strain energy to the thermal energy. So, the damping model for this kind of system is called a hysteretic damping. Okay. There are several other forms of damping that is encountered by a system. So, but in many cases people model it by using linear viscous damping, and a good approximation is usually observed. So, with this we are done with the theory of damping. One point I want to emphasize, that damping is a dissipative force which takes away energy from the system, and if a system has damping, then the conservation of energy does not apply to the system. We have to always consider the dissipative force if we are considering the conservation of energy. Second, most of the real cases are under damped. Critical damping and over damping are rare cases, and linear viscous damping is probably one of the most common form of damping. So, let us now go into certain examples. So, let us go to the first example on the under damping of a single degree of freedom system. So, here the problem is stated in this way: the vibration amplitude of an underdamped, I missed this term, this is underdamped, okay, of an underdamped single degree of freedom system decreases by half after 5 cycles are completed. So, assuming that the system is viscously damped, calculate the damping factor zeta. Okay. So, how do we solve it? So, in the previous theory on logarithmic decrement, we had measured the amplitude just after 1 cycle, but here the problem is given that the amplitudes are measured after 5 cycles, and after 5 cycles it is seen that the amplitude decreases by 50% or the amplitude becomes half. So, let me try to solve this problem. So, u1 at the initial time t1, let me write this as a cos omega d t1 minus phi into e to the power minus zeta omega n into t1. So, this is at t equals to t1. So, u2t, which is the amplitude at t1 plus 5 td, that is after 5 cycles, can be written as a cos omega d t1 plus 5 td minus phi into e to the power minus zeta omega n t1 plus 5 td. Okay. So, now let us try to simplify this. This is going to be a cos omega d t1 plus 5 into 2 pi by omega d minus phi into e to the power minus zeta omega n t1 plus 5 td. Okay. Now, this omega d is going to get cancelled with this omega d. So, I will have a cos omega d T1 plus 5 into 2 pi minus phi into e to the power minus zeta omega n T1 plus 5 Td. Okay. This can also be written as A cos, since 5 into 2 pi is going to leave us with omega d T1 minus phi into e to the power minus zeta omega n T1 plus 5 Td. Okay. So, let me now take the ratio of u1 and u2. So, if I take the ratio of u1 and u2, this is going to be A cos omega dt minus phi into e to the power minus zeta omega n T1 by A cos omega d T1 minus phi into e to the power minus zeta into omega n into T1 plus 5 Td. So, again this is going to get cancelled with this one, this is going to get cancelled with this one. So, I will have 1 by e to the power minus zeta omega n into 5 Td, which also can be written as e to the power zeta omega n 5 Td. Now, if I take the natural log on both sides, I have u1 by u2, which is my logarithmic decrement, and that is equal to zeta into omega n into 5 Td, which can be written as zeta into omega n 5 into 2 pi by omega d. So, this omega d can actually be written as omega n into 1 minus zeta square. So, this can be written as zeta into 10 pi by 1 minus zeta square. Okay. So, assuming lightly damped system, delta, which is equal to ln u1 by u2 in this particular case can be written as zeta into 10 pi. Okay. Now, it is said that u2 is nothing but 0.5 of u1. So, my del is ln u1 by 0.5 u1 because it has become half, and that is equal to zeta into 10 pi. Okay. So, therefore, ln of 2 is equal to zeta into 10 pi. Okay. So, therefore, zeta is nothing but ln 2 by 10 pi. Okay. If you evaluate this, you can find out the value of zeta. Okay. Right. So, this is how we can find out the damping factor even when the amplitudes are not measured just after one cycle, but measured after certain n number of cycle, where n is equal to 5 in this particular case. So, had this been n number of cycles, this would become ln by 2 into 2 n pi. Okay. So, let us, we are done with this example. Let us move into the next example, in which I will try to derive the equation of motion of a system, of a single degree of freedom system which has a damper. Okay. So that you know how to find out the equation of motion of a system with a damper. Okay. So, now this is the system which has a rigid bar. So, this blue color bar is a rigid bar of mass m. Okay. So, it is connected at a point O by a pin joint. So, that this bar is free to rotate about this pin joint. So, at a distance 3 L by 4 from the point O, that is the point of pin joint, a spring of constant K is attached, and at a distance L by 4 from the point O, a damper of damping coefficient C is attached to the system. Okay. So, now if I let me just draw the free body diagram of the system. So, if you are a starter on vibration, if you are just starting to learn vibration, it is always better to draw a nice free body diagram and then derive the equation of motion, which will minimize the error in finding out the equation of motion. So, let us see how the how the free body will look. So, say this is the line of equilibrium. Okay. And the so let the degree of freedom be the angle of rotation about the point O. Okay. So, this dotted line is the displaced position of the rod. Okay. And let us assume that it has deflected by an angle theta, which theta is my degree of freedom. Okay. So, since it has rotated in this way, the spring has been compressed. So, a spring force of K into this displacement is nothing but 3 L by 4 into theta. So, this is K into 3 L by 4 into theta, that is the spring force. This is my spring force. Okay. Let us see what is the damping force. So, the damper has slided in this direction. This translational displacement is nothing but L by 4 into theta. Okay. So, the damping force is going to be opposing the motion, and this is nothing but C into L by 4 theta dot. Okay. And an inertial moment is going to oppose the motion. So, let the moment is nothing but I 0, that is the moment of second moment of inertia about point O into the theta double dot. Okay. So, this is my inertial moment, similar to my inertial force. Now, if I do balancing of moment, I will get this as I 0 theta double dot, that is one inertial moment about O. I have to find the moment of this spring force about O. So, that is going to be K into 3 L by 4 theta, this is my spring force, into the momentum, that is 3 L by 4. Right. Then I will write the moment due to the damping force. The damping force will be C into L by 4 theta dot into the momentum L by 4, and that is equal to 0 since no external moment is acting. So, this can be written as I 0 theta double dot plus C into L square by 16 theta dot plus 9 L square by 16 into K into theta, that is equal to 0. So, we can find out I 0, and that will give us the equation of motion of the system. So, this is the answer. So, let me also try to find out I 0. So, I 0 about the centroidal point is m L square by 12 and then m d square, which is m into L by 2 minus 3 L by 4. So, 3 L by 4 minus L by 2 whole square, which should be giving me my I 0. So, so that is all for today's lecture. So, in the next lecture we will solve another problem on damped free vibration of single degree of freedom system, and thank you.